everybody, and welcome to Lesson 3.2, Human Population Dynamics. The content in this video is aligned to the third edition of Environmental Science for AP and covers information from College Board Units 3.3, 3.5, 3.6, 3.7, and 3.8. In our last lesson, we talked about how we identify populations and the way in which they grow. We'll continue that conversation in this lesson, focusing here on humans. Here is our content objective for this lesson. We're looking at how populations change over time in reaction to a variety of factors. At the end of this lesson, you should be able to do the following. Explain how resource availability affects population growth. Explain factors that affect total fertility rate in human populations. Compare and contrast total fertility rate and replacement fertility rate. Explain how human populations experience growth and decline. Explain survivorship curves. Identify an organism's survivorship curve as it relates to their reproductive strategy. And explain age structure diagrams. All of this is designed to answer the question, why do human populations grow the way they do? As we learned in our last lesson, population growth is affected by a combination of biological, genetic, and ecosystem interactions. We know that resources like food, space, mates, and water, those density-dependent factors, play a large role in population growth because as those resources increase in abundance, populations grow more quickly. In R-selected organisms, this can increase exponential growth and lead to a boom-bust cycle. In K-selected organisms, the abundance can lead to overshoot of the carrying capacity, leading to the oscillation of overshoot, die-off, overshoot, until the population settles around its carrying capacity. We also know that disease, another density-dependent factor, plays a role in population growth and can be connected to species interactions like parasitism. Competition and predation or herbivory, depending on the type of organism being consumed, can serve as a population growth control as well. It's important to note that all of these factors are dependent not only upon density, but also population size and dispersion. Populations with a clump dispersion are going to be more quickly affected by things such as resource availability and disease than those that are more uniform or random. One of the things we can do to understand how populations grow is to look at them in terms of survivorship. Survivorship is the proportion of members of that species or population that survive a given period of time. Typically, we're looking at the end of the natural lifespan. Once we have enough data over years of observing populations and using mathematical models to predict survivorship, we develop what are called survivorship curves. On an XY axis, where X is age or lifespan and Y is a logarithmic scale, we see three general patterns of survivorship emerge. They are categorized as type 1, type 2, and type 3. Type 1 survivorship is also known as a late loss curve because individuals with this pattern survive infancy or early stages of growth and adolescence at higher rates, but die the closer they get to their natural lifespan. This means that the majority of organisms are able to survive well into adulthood. Common type 1 organisms include great apes, including humans, elephants, and whales. Type 2 survivorship is known as a constant loss curve because individuals have a relatively equal chance of dying at any point in their lifespan. This means that there's no guarantee that surviving infancy or early stages of growth will lead to surviving into adulthood. Common type 2 organisms include songbirds, coral, and squirrels. Type 3 survivorship is known as early loss curve because individuals have a greater chance of dying at the early stages or infancy, but are likely to make it to the end of the lifespan if they survive those early stages. Common type 3 organisms include most insects and most plants. You may also hear survivorship discussed in terms of mortality as well. Rather than looking at the proportion that survive, mortality looks at the proportion that die at any given point. Notice that there is a correlation between reproductive strategy and survivorship, but it is not a clear black and white connection. K-selected organisms tend to demonstrate type 1 survivorship, while R-selected organisms demonstrate type 3. However, there are a multitude of organisms in both categories that demonstrate a type 2. Everything we've talked about at this point is related to biological populations that are subject to boom-bust cycles or measurable carrying capacity. Human populations, however, do not follow those normal patterns. This is known as the human paradox, where we are a case-selected organism that exhibits all of the characteristics of being subjected to density-dependent factors and carrying capacity, and yet we continue to exhibit exponential growth. While the graph of our population should take on the classic S-curve, when we graph human population, it looks like the J-curve of an R-selected species. This graph shows human population growth from the early years of civilization, approximately 2 million years ago, to 2010. And looking at the graph, we can see several consistent patterns. For example, for the majority of human history, the population has been exceptionally small and steady. One of the first blips of growth rate came with the discovery of fire, which led to better defense and the ability to cook one's food. But this growth was a small thing compared to what followed. Population growth experienced its true first boom with the Neolithic Revolution, around 8000 BCE. Also known as the Agricultural Revolution, this period allowed for settlements and urbanization, greater caloric intake, and a more steady food availability. It's after that that population begins to grow, though still by small measures. By the end of the Middle Ages, particularly with the invention of various types of mechanization, the human population was just under 1 billion people. At this point, population growth took off, leading to exponential doubling in a short amount of time. This is largely due to the Industrial Revolution of the 1700s and 1800s, which provided work, easier access to food, accelerated resource use, and access to advanced nutrition and the beginnings of modern medical care. By 1900, the human population reached 2 billion people. Notice that it took approximately 200 years for the population to double from 1 to 2 billion. By 1960, the population was 3 billion. Just 50 years to add another billion people. By 1975, we had 4 billion, then over 5 billion in 1990, 6 billion in 2000, and now almost 8,000 in 2020. The rate of population growth is accelerating, reducing the amount of time needed to double the population. This growth pattern that we see is uniquely human. Let's look at all of that from a different perspective. On the day of this recording, the human population was 7.84 billion people. On average, that means that number increases by 1.3 million people every 5 days. This means that there are around 2.1 million births and 800,000 deaths every 5 days. What other organism reproduces so fast, yet requires long maturation and extensive parental support? How have humans been able to do this? One of the reasons why is that we don't have a clear understanding of the carrying capacity of the planet for humans. Some scientists argue that there isn't one, that our ability to innovate with technology will continue to provide the resources that we need to continue thriving as a species on Earth. Other scientists argue that the human population long ago surpassed our carrying capacity, and that we are due for a cataclysmic population crash as land becomes less arable, disease runs rampant, hunger and starvation decimate various countries, and our actions have led to a climate change that poisons our atmosphere, our water, and burns through our forests with greater intensities. The truth is, Homo sapiens are a young species in the history of this planet, and our ability to measure the long-term effects of our population growth is still unknown. Are we subject to factors such as land availability, climate, and freshwater access? Do these limiting factors really play a substantial role in determining the point at which the Earth can handle no more humans? There's no clear answer to this. Many point to innovation and say that we are beyond limiting factors and carrying capacities. Others argue that the impact we have on the natural world should be a limiting factor on its own. After all this, we have to wonder why humans demonstrate exponential growth, and a rate that is accelerating with time. Are we simply at the start of our S-curve, demonstrating that exponential growth in the face of abundant resources? Will a time come when our resources become more scarce and we settle around some as yet undetermined carrying capacity? The truth is that we don't know. Our ability to use technology to solve problems makes humans a unique species. one for which it is impossible to predict the future with any certainty. However, some have tried. In the late 1700s, a clergyman philosopher named Thomas Malthus presented his model of population growth. Now, it's important to note that his model was based on observations of Irish populations who were considered second-class citizens in Europe at the time, and that he advocated against social programs that helped the poor, as he thought their starvation was a natural consequence of rampant reproduction. Basically, Malthus argued that food production had linear growth, and that production would grow and population would grow exponentially. For some time, there would be more than enough food to feed the population, a period of surplus that would lead to faster population growth. Then, a population growth would exceed our ability to produce food, leading to scarcity. The point at which this happens is called the Malthusian catastrophe. Even in Malthus's own time, innovation in agriculture and our beginning understanding of sanitation pushed that catastrophe point back further. It's possible that we are continuing to do that today, but the future is still unclear. Okay, that was a lot of heavy existential thinking. Let's break that up with a little bit of math. Here are 4 new equations that you should memorize. From lesson 3.1, you should memorize the population density equation, which, if you remember, is just the number of organisms divided by area, usually in square kilometers or hectares. To identify the actual number by which a population changed at any given time, you should use the raw population formula. This formula takes births plus immigrations and then subtracts from that deaths plus emigrations. To understand how a population grows annually, not by individuals, but by a percentage or proportion of the population, you would use the annual growth rate formula. That formula is crude birth rate minus crude death rate over 10. Crude birth and crude death rate are all measured per 1,000 individuals. So by dividing by 10, you're able to get a percentage. The growth rate formula can be made more precise by looking at immigration and emigration, but that is beyond the scope of APES. Notice that both raw population and growth rate can end up as negative values. What is the significance of this? A negative value for either of these would indicate that a population is shrinking, either by a particular number of individuals or by a proportion of the population. We can also predict how long it will take a population to double using a simple practice called the rule of 70. Demographers have calculated that a population growing at 1% per year will take approximately 70 years to double. This is used as an approximation by dividing 70 by the annual growth rate. Make note, you should always leave the annual growth rate in percent form. For example, if your AGR is 2%, you divide 70 by 2. Not 0.02. This is important, so be mindful of it. Also, doubling time cannot be a negative number. Typically, if a population has a negative growth rate, doubling time is not calculated. Lastly, you have fertility rate, which is simply the number of births divided by the number of women in a population. You should be familiar with these and be able to apply them not only in your labs and class tests, but also on the AP exam. Let's take a deeper dive into that last equation, the one that deals with fertility rate. Measuring fertility rate tells you a lot about populations overall. Areas with high fertility rate often also have low life expectancy, high infant mortality, and low quality of life. While not always 100% accurate, most countries that have high total fertility rates, or TFRs, tend to be developing or lesser developed countries, known as LDCs. Looking at the current numbers on this graph, indicated by the darker blue line, we can see that Niger actually has the highest TFR, with an average of about 7.5 births per woman. Sub-Saharan Africa tends to be the area where TFR is the highest, although parts of Latin America are not far behind. You'll see that the graph also presents information on a global average fertility, which in our current timeline is around 2.5 births per woman. This is very close to the value that we know as replacement fertility rate, or the number of offspring required to maintain a constant population size. Globally, this value is 2.1 and takes into account infant mortality and those who choose not to have children. Developed or more developed countries, MDCs, typically have TFRs that are very close to the RFR. This is because of increased industrialization and access to quality of life services such as prenatal care. TFR is a major player in population growth, particularly in developing countries. The factors described here also affect developed countries, but often not to the extreme as seen elsewhere. These 7 factors are key features of why populations grow the way they do, and ways to manage that growth. Religious practices and beliefs play a large role both individually and culturally. One's religion may advocate for having a large number of children, such as the Latter-day Saints, or prohibit the use of contraception, like Orthodox Catholicism. These practices can and do factor heavily into a woman or family's decision to have children. One of the major components that affect fertility rate is also healthcare access, used here to mean pre- and postnatal care, as well as care throughout the lifespan. Adequate care can reduce the infant and child mortality rates, as well as make childbirth safer for the mother, encouraging more births. Additionally, family planning resources are closely tied to healthcare. Being able to access family planning services, such as contraceptives or elective abortion procedures, can lead to the reduction in unplanned pregnancies and slow population growth. Both healthcare and family planning access can be impacted by government policies. Policies that provide for universal health care and access to safe medical procedures can encourage a limiting of births. However, these policies can also come in a more obvious way. Until recently, China had the one-child policy, in which a couple could only have one child. There were exceptions, of course, such as being allowed to have a second child if the first was a girl, but this was a practice heavily enforced by the Chinese government. Fines were levied against those who had more than one child. Female infanticide was high, as males have a greater standing in Chinese culture. This practice has been repealed, but the government still tries to encourage single-child families by offering a stipend to those who only have one child. And this leads us to our next factor, economic concerns. Having a child is expensive. Most estimates indicate that raising a child from infancy to adulthood could be anywhere from $250,000 to $500,000. This cost can form the choices of women and families to have children. Sometimes families who cannot afford to raise a child can give them up for adoption or put them in foster care. The last 2 factors we'll talk about are entwined and specifically aligned toward women. Providing women access to secondary and post-secondary education and providing a place for them in the workplace often leads to women putting off having children till later in their lives. One of the key takeaways from this is that providing resources to women can provide the easiest and most direct pathway to population control. Okay, take everything we've looked at to this point. We can look at population patterns to make predictions about future growth. One of the ways we do this is through population pyramids, or age structure diagrams. These diagrams can tell us multiple things: the sex ratio, the age distribution, life expectancy, infant and child mortality, that we can use to predict how population will grow in the future. Let's take a look at these. First, it's important to understand the axes. The graph has the x-axis between 2 sets of data. It is measured in age by cohorts, often in ranges of 5 years. The y-axis is positive in both directions and is measured either in raw population numbers or proportion of the population. Males and females are represented on opposite sides of the x-axis. Within those male and female data sets, there are 3 larger cohorts: pre-reproductive, typically ages 0 to 15, reproductive, 15 to 45, mostly to account for the female reproductive years, and post-reproductive, 45 and up. Understanding these cohorts allows us to predict how a population might grow in the future. A population like the one in graph A that has a large pre-reproductive cohort compared to the other cohorts can indicate future population growth at a fast rate. The opposite is true for populations like the one in graph C. We can categorize age structure diagrams in one of 4 categories based on their growth rates: rapid, slow, no, and negative. Rapid growth rates seen in countries such as India and Nigeria have large pre-reproductive and reproductive cohorts compared to post-reproductive ones. Slow growth shows a slightly smaller pre-reproductive cohort group compared to reproductive cohorts, although it is still numerous. The United States and some countries in Latin America have these kinds of population pyramids. No growth or constant growth has cohorts that are relatively equal in their proportions. Countries like China are moving toward a constant population growth. Lastly, negative growth has a pre-reproductive cohort that is significantly smaller than the other cohorts, leading to a future decline in population. This is best seen in countries such as Germany and Japan. The following slide provides you with an opportunity to see how some of these ideas are connected together. Feel free to pause the video and explore the connections between the topics. Then use the statements at the beginning to review.